Is it working?
Yeah.
I guess, yeah, okay. Thanks.
Okay, so please let us know about constraints for conformal defects.
Thank you, and first I'd like to thank the organizers for inviting me and giving me the opportunity to give a talk. It's my first time in IGST and it's been a lot of fun, at least so far, we'll see. Okay. The most of the talk will be based on collaboration with Amit and Deliang, but one of the examples that I'll cover in more detail will be based on work with Victor, Ben Deguz, and Jieshin. So I don't think I need to convince people in this room that defects are important to study. They are kind of ubiquitous in physics. They appear across many physical systems. I guess the examples that people care about most in this room are Mendelssohn line, for sure, but and also Wilson lines in ABJM. But I think in most rooms, probably this modified side, this impurity example is the most familiar one. Anyway, a p-dimensional defect breaks the conformal symmetry group when the defect is flat. It breaks the conformal symmetry group down to this conformal symmetry group on the defect and rotations around the defect, right? So the symmetry you'll see very manifest, the one that is easy to use is the smaller symmetry group that you've broken things down to. But I'll try to explain today how you can still take advantage of the full conformal symmetry group. So let me jump to the main result first and then get into the details. So the main takeaway should be that if we look at this type of 4-point functions where we have two operators, these are defect operators inserted on the defect. So, sorry, I should say this is specific to lines. We haven't worked out the higher dimensional case. Maybe I'll comment on that in the end. So this is now specific. We're specified to p equals 1. And in this case, if you take two generic defect operators inserted on the defect, OI and OJ, and you insert also two displacement operators, there are integrated correlator constraints on this type of functions. So these are 4-point functions. You multiply them by some kernel, you integrate, and there are some numbers that have to come out on the other side. These are the implications of the broken symmetry. So these were worked out in some way in Chern-Simons theory before, but most of what I'll say today is based on our paper from this year. And I should mention that I think, maybe I should say it this way, the final kind of the main formulas that I'll present in a moment were also developed in I think conceptually slightly different derivation by another group. Nadav is here. I don't think I saw Zivan, but you can ask them about this if you want. Okay. So these are the final results. So these F's are, as before, just the 4-point functions depending on the cross ratio. And these kernels, we call them homogeneous because the right-hand side is 0. And there's a very simple polynomials that you multiply, integrate, and you have to get the result on the right-hand side. And another set are the inhomogeneous constraints. This is because you have something non-zero on the other side. So this is the spin representations of this operator O. And this delta O is of course, it's conformal, is SL2R dimensions. And now the kernels are slightly more complicated. Sorry, yes, thank you. So lambda is the 2-point function of displacement. This is kind of the normalization of the displacement operator. It's an unambiguous quantity for defects. And typically easier to calculate than 4-point functions. So the reason it appears, of course, is because this F is canonically normalized. So if you insert two displacement operators and integrate them, you're going to get the canonically normalized 4-point function times the normalization. So before I jump into the derivation, this was tested, at least by us, in this set of examples. Okay. Yeah. Okay. I will get back to this in a moment. So there's been quite extensive tests of these constraints. Okay. Good. So let me explain the derivation. So I heard Shai talk to a master student on Zoom before, and he was explaining how to derive conformal identities for local operators, and I think it's good to review this. So we all know from the yellow book that, for example, that this identity in the first line should be satisfied for any local operators. And this becomes useful once we combine it with the second line, where we know the transformation of a local operator. This is just some conformal factor appearing. So we can try to do the same thing for lines. So let's say we have a line operator with some 2 insertions of operators on the line, and the first line is kind of the equivalent of the first line of the previous slide, and the second line should be the equivalent of the second line of the previous slide. Now here, a very non-trivial kind of piece of information is that we can remove this prime from W, from the Wilson line operator without paying any cost in terms of a conformal weight. The way to understand this is that any conformal transformation, kind of global conformal transformation, locally close to some portion of the Wilson line, looks like a global rotation, translation, and some SL2R transformation. And an SL2R transformation, we know the line doesn't transform under. So this is, if you want, this is another definition of the fact that the defect is conformal. Good. So we arrive at this identity, but this identity in this form is not extremely useful, I guess. Not many of us try to write down correlators on curved defects. They also depend on infinite amount of information. And I wouldn't know how to use this, so this is why this says derivation component number 1. We need to combine that with another component, which is essentially irrelevant perturbation theory around the straight line. So any curved line expectation value with insertions or without insertions of operators, I can express in terms of straight line observables where I have more and more operators inserted. To second order, it's roughly just integrating the displacement operator twice. This V, which is the difference between the profile of the line on the left-hand side and the straight line profile, will be our kind of space-dependent irrelevant couplings, if you want. And good, there are also counter terms where there are more powers of V and other operators that can potentially have the right quantum numbers to appear. So in principle, this framework of irrelevant perturbation theory has, as you go to higher and higher orders, more and more kind of unknown Wilsonian coefficients that you need to, that introduce ambiguities. But now when we combine the two, so we combine the ability to expand both sides in this irrelevant perturbation theory together with this identity, which is a functional identity, right? It works for any profile V of the line. We can fix all of these irrelevant coefficients in this, all of these ambiguous coefficients in the irrelevant perturbation theory. So the point is that we gain kind of predictive ability to write down the expectation value of a line as we deform it. And this is not all we get from studying this identity. So also when we study to second order, we get all of these integral constraints, all of these integrated constraints that I wrote down before. Now, maybe I should point out this is a little bit like hitting a nail with a sledgehammer, in the sense that we have an infinite set of identities above. It's a huge set of identities, and we get only a finite set of identities in the end because we just expand this to second order. So in principle, this can be expanded to higher orders. This should include many more identities that should be satisfied for straight lines. But it becomes kind of algebraically more and more complicated to do this. So in Chern-Simons, we went to third order. In Chern-Simons coupled to matter, we went to third order, but there we already knew the 4-point function at that point. So it's kind of just testing that this framework works to the next order, but not really getting new constraints out of it. Okay, so back to the tests and examples. I'm going to briefly explain 3, 5, and 6 maybe. I don't know, how much time do I have? 20 minutes. Okay. Should have went slower. What? Sorry? Yes. Okay, great. No, that's good news. Okay. So first, maybe I should say why I won't review the n equals 4 example, which might be the most fitting for the room in a lot of detail. And the reason is that, in a sense, it was done before. So in n equals 4, the displacement and the tilt operator are in the same multiplet. And maybe I don't remember if I said it, but on the previous slide I said that the constraints for tilt operators were already derived before we derived these constraints for displacements. And in principle, we were guaranteed to succeed as long as our derivation is correct. These constraints, kind of the cousins of these constraints when you translate your displacement 4-point function into tilt 4-point function using supermultiplet was tested before. So it's still a good test that the derivation is correct, but not maybe a new result in a full sense. Another example that maybe is familiar to the room is the 2D CFT that is dual to ADS3 times S3 times T4. So in this case, we have one parameter, which is the ratio between NS and S and RR flux. And we can study the kind of the defect that is dual to the stable string configuration in this background. One way to get the 4-point function of displacement is by studying fluctuations around this setup, and this 4-point function that you get satisfies these constraints. It's quite straightforward to test. But maybe one comment that I should make is that in this case, there is another way to try and get the 4-point function of displacement, which is a bootstrap approach, where you have some general ansatz for the 4-point function, and you try to fix it using fix the coefficients using supersymmetry and conformal symmetry. And in that case, you get everything fixed up to conformal symmetry of the defect. It's only on the defects SL2R. And in that case, you can fix everything up to two unknown coefficients. And if you plug this into the constraints that I presented before, you can fix one of these coefficients. So in a sense, it completes this bootstrap approach. The other coefficient you shouldn't expect to fix because it should be essentially the ratio of RR and NS flux, maybe renormalized in some way that you will not be able to fix. Good. Now I will view a bit in more detail the last example, also because I think this is a setup that hasn't really been studied before a lot. This is planar pure Young Mills in ADS with a Wilson line on the boundary. Okay, so this is this is QFT in curved space, not a holographic setup. So first, let me say why we would care about such a thing. So if we start with planar pure Young Mills in flat space and we take a probe quark and anti-quark, or a Wilson line and anti-Wilson line, or Wilson line going up and down in time far from each other, between them there will stretch a flux tube that it can be well approximated at low energies by effective string theory. Now, the fluctuations of this effective string can be studied using Nambu-Goto action plus corrections that incorporate curvature invariance and extrinsic curvature invariance. What kind of remarkable that was verified using lattice studies is that up to roughly QCD scale in 3 dimensions, this effective theory works pretty well. So you just need to tune a bit the Wilson coefficients, but there are no new degrees of freedom that you have to integrate in for the effective theory to continue working. And in 4D, roughly the same thing happens. You just need to add 1 degree of freedom, which is a pseudoscalar, a massive pseudoscalar, and people refer to as the worldsheet axion. And then, again, the effective theory works pretty well. So yeah, maybe I should mention, since Shota, as I think said yesterday that I will mention it. I wasn't planning to mention it, but in principle, there are integrable theories that are close to both of these theories. So close is kind of a phenomenological statement here. But in 3D, there's an integrable theory just for the Goldstone scattering that is quite close. And in 4D is a theory where you have the massless Goldstones and also a massless pseudoscalar, which has roughly the same coupling as this massive axion, but is massless. Now, okay, so the question to be asked is, what more can we learn about this theory? And one of the hopes was that asymptotic freedom can tell us something about its high energy limit. Okay, but if you just study high energy scattering, for example, that has a lot of UV-IR mixing. So it's not something that you can easily isolate and compute using asymptotic freedom, for example. So our way of trying to cure this is by putting the theory directly inside ADS space and curved space. So this setup has 2 limits. Okay, there's maybe a lot of information on the board, but we put the theory inside ADS space with Neumann boundary conditions, with Neumann boundary conditions, general expectation in the community is that there is no deconfinement phase transition as you change the radius. This is unlike the Dirichlet boundary conditions, where at small radius you have a conserved current on the boundary, so you must have a deconfinement phase transition. And if I add these Wilson lines on the boundary, I have this funny situation where at large radius I have the confining string stretching between this kind of source and sink of flux. And as I take the radius to be smaller, as I cross roughly lambda 1 over lambda QCD, the ADS geometric confinement takes over. And the string is not even allowed to grow up to size 1 over lambda QCD because of the geometric confinement. So even if I put a non-confining gauge theory in ADS, I will get this kind of fluffy string in the beginning, but this line will just stay straight, this string width in units of radius of ADS. What happens in the confining theory is that at some point it starts becoming smaller in units of radius. Good, so this is a setup that we would like very much to study because we have one limit, small radius, where we can compute things in perturbation theory and use the UV description of Young-Mills. And there's another limit in large radius where we have the effective string, and we would really like to combine, kind of understand how these degrees of freedom reorganize into those degrees of freedom. But unfortunately, computations in Young-Mills, sorry, maybe I should say, so one thing we would imagine plotting eventually down the line, at least on some qualitative level, is a plot like this, where we have the spectrum of one on one side, the other spectrum on the other side, and we try to understand how it evolves with the radius. This is in 4D. This is kind of how it should roughly look in 3D. So these are just impressionistic paintings. It's not any result. So you might hope to start doing computations using the perturbation theory, for example, but of course this is not so easy because these are Witten diagrams, and at least for me, it's very hard to do any computations with Witten diagrams. We managed to compute the 3-point function after some efforts. So we have OP coefficients of operators of this form, derivative, kind of perpendicular derivatives of f inserted on the line. But going any further than this was hard, for example, getting anomalous dimensions. So here come kind of these constraints that we had before. Let's try to use them in this case. So let's compute the 4-point function perturbatively and try to plug it into the constraints. For example, the homogeneous constraint that I presented in the beginning. And the first two give some O1 number that does not satisfy the constraint. We integrate them with this kernel, and we get something that is non-zero. That doesn't make sense, right? But it turns out that the reason for that is that the perturbative expansion does not commute with the integral appearing in the constraint. Okay, so if we are not allowed to first integrate the 4-point function and then plug it into the integral. We have to first integrate and then perturbatively expand kind of the result in terms of conformal data. And this can be done with some care. The reason for that is that this t to the n comes from the kernel itself. This t to the 4 minus delta you can imagine being some cartoon for the exchange of some operator. And once we integrate this, we get some number over an integer minus the dimension, and you can imagine that at weak coupling, dimension becomes integer, and you get a pole that goes like 1 over the anomalous dimension. I think maybe someone mentioned that already. The same thing happens in the bootstrapability papers, so maybe it's familiar to some of you. So once we do take this into account, we have this minus 5 over 3 that comes from the naive integration of the O1 part, and we have this, we call it enhanced part, where something from first order comes and contributes to the constraint already at O of 1. Something from O of g to the minus 2, something of O of g squared contributes already at O of 1. So we get this constraint, which allows us to determine some conformal data. If we do the same thing for the homogeneous equation, in homogeneous equation, we can actually fix all of the conformal data. Lambda is the same lambda that Chai asked about before. It's a 2-point function of displacement, and we know it. I was just too lazy to plug in the value, but it's a free theory computation. It's very easy at this order. So you can do the similar analysis for the case where you have 2 generic operators and 2 displacement operators, and you get some annoying recursion relations that can be solved after a few hours of staring at them. And you get all of this conformal data just from the symmetry analysis of the problem, just from the broken symmetry analysis of the problem. So what's first thing you do when you get this, you look at these C's. This looks much simpler than the formula I had before. here, but actually it matches exactly to that formula. So that's, if you want, that is the sense in which this is a test of the integrated constraints. So the fact that the perturbative computation of the three-point function matches with this determination from symmetry. And then we have also a new prediction, which is the anomalous dimension, which is what we wanted from the beginning to be able to determine, and was very hard to do with Witten diagrams. So we are being, I guess, rewarded for looking at the symmetry more carefully in this case. So I think how much time? Sorry. 10 minutes. Oh, wow. No, okay. No, okay. I just, okay, I thought it would take me longer. But good. Maybe that means that a lot of people are confused, so some time for questions is good. But okay, let me then just say something about strong coupling. So at strong coupling, it's a bit harder to use these constraints to predict something. So first of all, we have an effective string action at strong coupling or large ADS radius. We can use the effective string description. This allows us to compute a three-level four-point function. Basically, it's exactly the same as in n equals 4 to this order, because there is in n equals 4 the scalars do not mix in this order, so we can are decoupled at this order. So it's really the same result to three-level, and we might hope to be able to get one loop. So this is done using technology that was developed in this paper. Most papers, mostly in the paper by Forini and Bonomi, where we can use a dispersion relation based on the Lorentzian inversion formula to compute, say, a regularized form of the four-point function. The sense from the regularized four-point function, we can get the original four-point function by adding some information about low-lying operators. So, okay, I don't want to review their work, but in principle, this is something that is understood in the literature and allows us to plug in the three-level data and get the one-loop four-point function up to some low-lying CFT data that is left unfixed. And this is perfect if you have a integrated constraint, right? Because you can just integrate the expression that you got and try to fix these unknown coefficients. And it turns out that at one loop, you can fix the displacement four-point function up to one unknown parameter for this specific theory, this Young-Mills theory. Good. And you cannot hope to do better because there has to be some parameter that tells you in which dimensions you are. So actually, you can, everything I said, maybe I forgot to say, everything I said was for Young-Mills in 3D, the simplest setup you can imagine, Young-Mills in 3D ADS. But you can set up exactly the same setup in 4D, 5D, 6D ADS. And well, I guess you don't get confinement at some point, I think. But in 4D, you can do the same thing. And you should have exactly the same constraints on the four-point function. The analysis is the same, so you better have one unfixed parameter that allows you to go between 3D and 4D, right? So one value will correspond to 3D, and another value will correspond to 4D. OK, so let me just quickly summarize the results. So line defects, generic ones, satisfy a set of integral constraints that I presented. They are quite explicit. They were extensively tested. For ADS 3 times S3 times T4, we can use it to kind of complete the bootstrap determination of the three-level scattering, and four-point function. And for pure Young-Mills in ADS, this allows us to determine a host of stuff, a bunch of conformal data. We hope that even this will help us go to higher orders in perturbation theory eventually by combining this with the dispersion relation coming from the inversion formula. Now, in terms of future directions, I think there are many of them. There are some that are quite straightforward, and the reason I say this is because I think we need to be motivated in order to pursue them. So, for example, higher dimensional defects, I at least don't know of many examples in the literature where we can get the four-point function of displacement, so to test such a thing. So it's it would be very nice if there is a clear motivation for any of this direction, either higher dimensional defect or to include bulk operators, for example. That's also a straightforward generalization, or for interfaces of boundaries. In terms of directions where we are actively working on, they are here, and if any of you wants to ask me about any of them, feel free. I'm not going to say too much about them, I think, at this point. Maybe the first one is just that what I mentioned before, that in principle we have this identity that involves any shape of the line on the left-hand side and some other shape on the right-hand side. And we can expand both of them around the straight line. And at least I don't see how this does not encode a lot more symmetry, and I would like to understand the structure of this thing when expanded around the straight line in terms of the algebraic structure. Okay, maybe I'll stop here.
Questions to Barak? Yeah, Daniel?
Maybe the last thing on the motivations on improving mark operators. Before we mentioned that when we differentiate with respect to the coupling constant, we have an integrated action. And would that somehow be a justification for studying the involving mark operators to see how this dependence unfolds and we can get some corrections, so-called Gaussian inverse insertion method for
what you can get, right, is some, okay, I don't know if I talked about this with you. I don't remember with who. So for a defect with no insertions and one bulk operator, in principle, this was worked in Marco's paper, Marco and others from 2016, where you can relate the 1-point function to the 2-point function with the displacement operator on the line. Beyond that, I don't think anything has been worked out. I don't know how that would help in the case that you are. So maybe this has some implication in the case you described. It's not immediate for me, but might be worth looking at. But I don't see any immediate. In principle, the reason that you would be maybe not immediately inclined to just sprinkle some bulk operators is just because then the kinematics become very complicated, right? But if you have some very specific system that you want to study, then you can probably use this type of where you, yeah.
Can I ask something? I mean, in recent developments in the spectrum discussion in N=4, you get that, well, you kind of know that the perturbative expansion and recoupling determines the whole story because it's having like a finite radius of convergence. But then when you try to go to strong coupling, I mean, people have these trans series questions and add in all sorts of things. I mean, as far as I understand, you say I do at 2 loops I have 2 V operators inserted, and at 3 loops there will be 3 and so on, and that's a recoupling expansion. But like for any theory, can I just naively apply this logics to a strong coupling expansion?
Sorry, so now we are, which context are we discussing? The Young-Mills context or the? Yeah,
I was just wondering, you had some comments on strong coupling. So okay. Do I think that the motivation that you gave at the beginning with these V operators for the identities you impose, is it valid or is it not valid?
Okay, sorry, let's, my comments about strong coupling, I think, were for Young-Mills, where it's strong coupling, we have a effective string description, and weak coupling, we have a perturbative description. I'm not saying one is valid all the way to the other. The hope is that there's some overlap in the validity region in the middle, and you can kind of extrapolate both or interpolate both. Say, have 2 or 3 orders from each side and try to have some the 2-sided Paderi summation or something like this to just get some qualitative understanding of how the spectrum changes. In the context of the derivation here,
yeah, right.
In the context of here I'm not assuming any weak coupling. If you want, I'm assuming, oh, you mean the V is weak, V is small.
Yeah, I mean, so that you get 2 V's for, so would the same thing apply at strong coupling? I mean, you just do effects with some inverse couplings or?
Okay, so maybe I should clarify here that V here is the coupling from the point of view of relevant perturbation theory, but this is the coupling here is how much you want to displace the line from the straight line. It can be a strongly coupled defect,
I get confused.
but it's no. So maybe I mean I did go too fast. So yeah, yeah. Okay. Right. So this it can be a strongly coupled defect. That's not a problem.
Right. Okay. Sorry about that. So is there some reasonable question?
Yes. Hi, Barak. I'm here.
Oh, hi. Yes.
So in the case of Young-Mills, and like a flux tube in ADS, if you insert more letters, then you can construct like open spin chain. So is there any possibility of extracting reflection matrix of that open spin chain from your computation?
Okay, so you have to do a bit of translation to what you said. So if you insert, so what is the setup?
So the idea is that you insert more Fs at the same time at the same location.
But still on the
Yes,
closed
yes.
Wilson loop. I insert many Fs. That perturbatively, it seems that we can determine. So what I determined so far is quantum numbers for a lot of derivatives on Fs. I can study operator with more F insertions, but I cannot fix all of the conformal data. It seems that I can fix everything up to maybe one number per number of Fs.
I see. So if you insert more Fs, then you can create an open spin chain.
Okay.
And then from there, I think like you might be able to, if you know the answer, you might be able to read off, for example, something like a reflection matrix.
So when you say the answer, you mean anomalous dimensions, for example?
Yeah.
I see. Okay, that's interesting. I think we can probably determine it perturbatively, to leading order in perturbation theory at least. So yeah, we can discuss this.
Anyone else? So if not, then let's thank Barak again.